Hello, in this video, we want to look at the idea of estimating the sum of a series. So suppose that we know we have a series that converges by the integral test. So this idea is going to work for integral test series. It doesn't work for others. But if we have a series that converges by the integral test and we want to find approximately what the sum is. Because again, the series and the integral do not converge to the same value. The values might be close, but they are not the same. And we want to find an approximation of the sum that we don't know, even though the integral test is working. So we're going to consider this series 1 over k cubed. We've looked at this before. We had 1 over n cubed. This converges by the p series test with p equal to 3 greater than 1, or because p is equal to 3 and greater than 1. And the sum of this series is going to be taking all of the numbers 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed and so on, and adding that up. We want to know, what is this number? So we're going to define some things to be able to figure out what is this number. So first thing we're going to define is what is known as the remainder. Suppose we have a series, and we're going to look at any series here, which is all those terms of the sequence added up. So we're adding an infinite number of things. All of these things added up to infinity is S. It is the sum. However, if we just look at the first n terms, we actually have a name for that already. We've called that S sub n, or the nth partial sum. The remainder of everything else that's not part of the nth partial sum is the nth remainder. Notice that the nth remainder starts at n plus 1. So this is a weird mental hurdle of, we're going to see this r sub n keep coming up, but we need to know that means the n plus 1 term onward. So the nth remainder is the n plus 1 term plus the n plus 2 term plus onward. It's the stuff that's not included in the nth partial sum. However, simple addition tells us that the sum is the nth partial sum plus the nth remainder. This also means that nth remainder, the thing we're just introducing, is the whole sum minus the nth partial sum. And in general, to get accurate sums, we want that remainder to be really small. If we're trying to estimate the sum of a series, which is what we're trying to do, trying to find an approximation, we want that remainder to be small. Even though we're adding on an infinite number of things, we want that remainder tiny. So we want to find a way of, how can I tell how big is this remainder? And that is where the estimation theorem comes in. This is the integral test estimation theorem. So I will repeat, this only works for integral test. If we use a later test on a series, the integral test will not help us estimate the remainder. This works for integral test series and integral test series only. So if f of x is something that meets the properties of the integral test. So if it is continuous, positive, and decreasing on some interval n to infinity, and the series a sub k converges, where a sub k and f of x are the same for whole number k values. Then, before we fill in this then, we're going to look at some pictures. We're comparing a series against an integral. So we're wondering about this n plus 1 term onward. We're wondering, how can I compare this remainder? So we have a continuous positive decreasing function, and the remainder takes r sub n plus 1 plus the n plus 2 term, say a n plus 1 plus a sub n plus 2 plus a sub n plus 3 onward. Well, this, using that idea of boxes, if I draw my boxes going to the left, then my sum is under this curve. And in particular, my sum is under this curve in such a way that that remainder term is less than the integral of f of x from, notice, since we drew our boxes to the left, we're starting at n. So the remainder is less than the integral from n to infinity. However, we don't always have to draw the boxes to the left. We could take this same idea where we have the remainder adding up those terms. We have the n plus 1 term plus the n plus 2 term plus the n plus 3 term, and so on. And instead of drawing our boxes to the left, we could use that same rectangle idea and make boxes to the right. And these are the areas a sub n plus 1, a sub n plus 2, and so on, a sub n plus 3. Now our boxes are above this curve. So this is bigger than our curve. But now, since we're still looking at the area under the curve, still going to infinity, but the area we're looking at starts at n plus 1. This means if we order these inequalities, the integral from n plus 1 to infinity f of x dx is smaller than the remainder term. And that remainder is smaller than n to infinity. And this means we have a lower bound and an upper bound. Meaning this remainder that we're wanting to be really small we can figure out what that remainder is by putting it between these two integrals. So let's return to our problem of the series 1 over k to the third. So returning to that problem, suppose we find the fourth partial sum of 1 over k to the third series. S sub 4 is those first four terms. That's 1 over 1 to the third, plus 1 over 2 to the third, plus 1 over 3 to the third, plus 1 over 4 to the third. This, if you put this into a calculator, works out to be approximately 1.17766203704. And now, that is just those first four terms. Comes out to be 1.17766203704. What are we throwing away from the 1 over 5 cubed plus 1 over 6 cubed plus 1 over 7 cubed? That's R4. This is that a sub 5 plus a sub 6 plus a sub 7 plus ... It's the stuff that's thrown away from our fourth partial sum. By our integral remainder theorem, we know we're going to look at the integral from the next term up to infinity and the integral from n to infinity. So the lower bound is the integral from 5 to infinity, the next term up, which is 1 over x cubed dx. I'm going to leave that as practice for you to work out. That's 0.02. And the upper bound is the integral from 4 to infinity, 1 over x cubed dx, which works out to be 0.03125. With the remainder and with our partial sum, we can actually now estimate an exact value for the series. Because we know our remainder, it is somewhere between 0.03125 and 0.02. Could be 0.03 exactly. It could be 0.028. Somewhere between those two numbers. And that's a very small window. So that is our remainder. As we saw up here, if I take my remainder and I add on my partial sum, that is the series. So I'm going to take my remainder, I'm going to add the fourth partial sum. The fourth partial sum, we worked out to be that long decimal, 1.177, so on. So we have 0.02 plus 1.77662. I'm going to cut it off at that 2. Which is less than R4 plus S4, which is less than or equal to 0.03125 plus 1 point. There's an additional 1 that starts off 1.177, 1.177662. And like we said, that is the sum. R4 plus S4 is the series. The series is between 1.20892, taking these two numbers and adding them together, and it's bigger than 1.197662. So it is between these two numbers. That is very close together, but it gives us a good estimate of this series. So ultimately, our series is somewhere in this 1.2 range. And depending on how many terms we need, we could make that more accurate. But for right now, saying it's somewhere in that 1.2 range is really accurate. Got a decent amount of decimal places to it. Now, what if we need to know a certain amount of accuracy? What if we had a series and we're going to change the series to give this example? What if we had a series and we want our estimation to have an amount of accuracy? This is where a lot of real world applications would come in of, I need this calculation to be accurate enough to make sure that this piece fits into this tiny hole that's created for it. Or I need to make sure there's enough accuracy that the structure I'm working with is holding. So suppose I need my error in estimation to be less than 1 over 10 to the 6th. Well, our estimation remainder, we're assuming this works with the integral test, and I can tell you it does. It will work with the integral test. By the integral test remainder theorem, the remainder is less than the integral from n to infinity of 1 over 2x plus 1 to the 6th dx. Working this out, this is the limit as t goes to infinity of the integral from n to t of 2x plus 1 to the negative 6 dx, which is, this integral would work out to be negative 1/5 times 2x plus 1 to the negative 5th times 1/2 by the u sub for that inside piece from n to t. Negative 1/5 times 1/2 is negative 1/10. Limit t goes to infinity of 1 over 2t plus 1 to the 5th minus 1 over 2n plus 1 to the 5th. Since we're worried about t going to infinity, that's just this first fraction. As t goes to infinity, that goes to 0. N is unchanged. N is still just this fixed number. So this integral works out to be negative 1/10 times negative 1 over 2n plus 1 to the 5th. The remainder is less than this function 1 over 10, 2n plus 1 to the 5th. And we want the remainder to be less than 1 over 10 to the 6th. So the remainder is less than or equal to 1 over 10, 2n plus 1 to the 5th, which needs to be less than 1 over 10 to the 6th. Taking the reciprocal of both of these fractions, this means 10 times 2n plus 1 to the 5th is bigger than 10 to the 6th. Dividing everything by 10, we get 2n plus 1 to the 5th is bigger than 10 to the 5th. Fifth root of everything, 2n plus 1 is bigger than 10. 2n is bigger than 9. And n is bigger than 4.5. Notice the strict inequalities. Also, n has to be a whole number. So n has to be bigger than 4.5. Well, if n needs to be bigger than 4.5, it can't be 4. It has to be at least 5. So we need at least 5 terms for r sub n to be less than 1 over 10 to the 6th. Remember, we are estimating the series so that the error is less than 1 over 10 to the 6th. So we need at least 5 terms. So to finally estimate, we're just going to find those first 5 terms added together. So that would be 1 over, plugging 1 in, we'd have 2 times 1 plus 1, 3 to the 6th. Plus 1 over, plugging in 2, 2 times 2 plus 1 is 5, 5 to the 6th, plus 1 over 7 to the 6th, plus 1 over 9 to the 6th, plus 1 over 11 to the 6th. This works out to be, if we were using a calculator, 0.00144668881. And there is our estimation. That is accurate to 6 decimal places. So that is the estimation theorem for integral test. We can find a small enough error to get an accurate sum. And we can also say, if I have this sum, how accurate am I? So finding an accurate sum with a small enough remainder versus how accurate is my series based on only using 4 partial sums. And that is the end of integral test. And remember, we also got in this section the divergence test and the p-series test. So we got 3 more tests.